Okay, so back to a little bit of graphing. And we kind of have to do this after we did the Hopital's rule because part of it's looking at limits, especially to infinity, to find some asymptotes. So that's why we didn't do this before we did the Hopital's rule. So there is a group of things that we can find given any equation that we have. The first thing that is always extremely important to find is the domain of the function. So that's where the values of x do not exist. Okay, so always the first thing you're going to look for is the domain. Now, everything, so it's actually kind of important because we've been talking about how before in pre-calc, you've basically been able to do pretty much all this stuff, but only for polynomials. And now we've expanded that to all types of functions. But function still is not every type of mathematical expression or equation, because we have things that are not functions. So the stuff that we're looking at with here works for functions. Okay, so that means one input, one output. So the next thing we want to be able to find is any intercepts. So your y-intercepts, your x-intercepts. Every function will have a y-intercept or the asymptote at the y-axis. So it's either going to cross the y-axis or it's going to have a vertical asymptote at the y-axis. And x-intercepts. So to find the x-intercepts, we set it equal to 0 and solve it that way. Sometimes very difficult to find exact x-intercepts. There are methods to do that, but at that point, just use a computer or a calculator to find that. Next, symmetry. So symmetry will help us find and create graphs because it allows us to find only parts of them. You saw this in pre-calc when you were looking at even functions and odd functions. Even functions are where the negative version of the x and the positive version of the x give you the exact same answer. So that would be symmetric across the y-axis. The odd functions were symmetric across the origin. So that means if you plugged in negative x, you got the negative y version. So it's symmetric about the origin. So basically both signs change. And then the other type of functions that we can have are periodic functions. These are most of the time your trig functions, sines, cosines, and whatnot. Those are periodic functions. However, you see here that sine of x is actually also an odd function that is symmetric over the origin. So just because it's periodic doesn't mean it can't be an even or an odd function. Your asymptotes. Three different types of asymptotes. Horizontal, this is where we're looking at the limits when you're going out to infinity. Okay. So that's where L'Hopital's rule could come into play, because if you can't necessarily find it, you might have to do L'Hopital's rule to figure out what happens as it's going to infinity. Vertical asymptotes, those are going to come around where you have your domain restrictions. So your domain restrictions are either going to be a hole in the problem if it's removable, or a vertical asymptote. And the last one we have is a slant asymptote. Slant asymptotes come into play when you adjust a function. And we'll see how Alex wants you to actually deal with those in the problems that we're going to look at. Which you saw, depending on how deep your pre-calc class got into it or your algebra classes in high school got into it, that is also when you have a rational function and the degree of the numerator is 1 more than the degree of the denominator. So when you do your long division on it, you get a linear equation as the quotient. And that would be your slant asymptote. All right, now on to the specific things related to calculus. Increasing and decreasing, that is your first derivative. So if it is increasing, your first derivative is positive. If it is decreasing, your first derivative is negative. Local mins and maxes, that is where your first derivative is going to be 0 or does not exist. Those were those critical numbers that we were looking for. So we can use the first derivative test for them. So if it's changing from a positive to a negative at that critical number, then it is going to be a local maximum. If it's changing from a negative to a positive at that critical number, then it is a local minimum. A lot of those you can get directly from a quick graph to see how they actually convert, or just plugging in a number on either side of those critical numbers, which is what we did. Last one, concavity and points of inflection. So your concavity is the second derivative test. If the second derivative is greater than 0 or positive, then it is concave upward, which looks like a smile. So it actually it's pointing down, but it's actually concave up. And concave downward, where it is the second derivative is negative. The inflection points are the critical numbers in those spaces. So that's where the direction changes. So you find your critical numbers, look at either side of it. That's where your points of inflection are going to come into play. Using all those, you can actually get a really cool graph of a function. Okay. Typically, in most situations, you are not going to find all those. But it is important to know how to find them. So this way, whenever you need a specific part of it, you know how to find that part. Okay. All right. So what we're going to look at is how Alex does it. All right. So there's 12 topics in chapter 4 that deal with nothing but sketching these graphs. And there's a variety of them. Some of them are like this. Some of them are just going to give you the function and ask you to graph it. And you're going to have to find this information from the table. However, I thought you could actually move this. Oh. There you go. Now you can actually move it. All right. Oh, by the way, I don't know if everybody knew you could actually do that. If you click this little arrow, it undocks it and you can move it. So you can actually have it on the same screen as your graph. All right, so the first thing they want us to graph is our points. So when you're looking at these, I'm going to take a let's look at each of these pieces, and then we will talk about what they do. All right. So these are your points. So anytime you have just an x equals and then the y in that first one, those are giving you your points you're going to graph. So in this case, I've got 5 points that I'm going to graph in this function. The other thing that this does, so the next piece are these. So these are going to tell you what is happening in between those points. So now, based on your first derivative and your second derivative, you should have an idea of what's going on in those intervals. So, between negative infinity and negative 11, what's this function doing? Is it going up or going down? Is it increasing or is it decreasing? We look at our first derivative. First derivative is positive, so that means it is increasing. And the second derivative is negative, so that means the concavity is what? Concave up or concave down? Down. So concave down. So that means it is increasing and concave down at that point. Why is that important? Because when you're looking at this problem, so let's graph the 5 points first. All right, so we've got those points. Now, each of these here are your curves. You have increase in concave down, decrease in concave down, decrease in concave up, and increase in concave up. So you need to figure out which one of those four you're going to choose at each of those points. So positive and negative is an increase in concave down. On this interval, we have a positive and a negative. So I'm increasing and concave down. On this interval, I've got a negative and a negative. So now I'm decreasing and concave down. Negative and a positive. Decreasing. And that's concave up. Positive, positive. Increasing concave up. Positive, positive. Increasing concave up. So now you know where you're going to click each of those points there, or values there. So let's go back to this. So on that first interval, it was increasing and concave down. So increasing, concave down. On the next one, it was increasing, concave down. And notice how it adjusts the curve for you as you're doing it. Next one, decreasing and concave down. Decreasing, concave up. Now, it says, okay, what's going on in this inflection point? That value right there will tell you what it's doing. If it's infinity, then if it doesn't exist, then it's this one. It's a vertical tangent line. If it's not, then it's a slanted tangent line. Because that means that that inflection point, it didn't exist. So it was actually straight up and down. Next one is, where was I? This one. Decreasing concave up. No. What is that? -4 to 0. Oh, concave it up. Oh. Hold on. Decreasing concave up. Oh, I already did that one. That's fine. Increasing concave up. I was looking at the wrong one. And then increasing concave up. So that's on this one here. And that's our graph. So you have to use their information to do it. You're not actually, notice how in this problem, they don't give you the graph. They don't tell you what the equation is. So you can't just go to Desmos and get the equation for it. You have to use the information they gave you. So look at the next one. Oh, so this one. All right, so now this one, they give you the equation. So you need to find that information from that table. So what was the information that it gave us first? What was the first thing we graphed? The points. Which points? So if we looked at it, the last one, the points that they gave me were my intercepts and were the minimum and maximums. We might not be able to find the minimums and maximums yet because I don't have that first derivative to figure out where those are. But I can find my x and y intercepts. So how do I find my x and y intercepts? All right, let's take a step back and do this one at a time. How do I find my y-intercept? What was it? For y-intercept, I plug in 0. Now, notice if you did this on a calculator, a lot of times you're going to get a fraction or a decimal answer. And it doesn't want a decimal answer. It says use exact values. So that means there's a very good possibility when you're doing these, if you get a full decimal answer, you're probably going to have to do this out by hand or some other way to get the answer. So if we plug in 0, what do we get? What's f of 0? It's just 0. Okay, so my first point is 0, 0. And that's the y-intercept and the x, one of the x-intercepts. All right, now how do I find my x-intercepts? Solve it for 0. All right, how do I solve this for 0? Okay, so I've got 2, right? So I got negative 16 over 15, x equals 0. So I set each factor equal to 0. So this one is just x equals 0, which is the one I already have. And this one x equals 2 square root of 5. You wouldn't have got that as a plugging it in. All right. So we can graph those 2 points. When you're plotting these points, it gives you this full capability of options here. So I can put 2 square root of 5 and 0. All right, so we found our intercepts. Is there any domain restrictions in this problem? Is there any values that won't work? Because that'll give me my vertical asymptotes or hold, right? Are there any values that won't work in this problem? What's the domain restrictions? We have can't divide by 0. What else? Square root of a negative number or an even root of a negative number. So I don't have any divide by 0 in this problem. I don't have any square root of a variable in this problem. I don't have any logs in this problem. So there's no domain restrictions. I'm probably not going to have a vertical asymptote in this problem. All right. Horizontal asymptotes. If you plug infinity into this, what are you going to get? Huh? Well, yeah, I'm going to get negative infinity times infinity, so negative infinity out of this. So that means it's going to a negative infinity that way. And if I plug in negative infinity, I'm probably going to get positive infinity. Actually, no, I'm going to get negative infinity because of the cert. So therefore, there's no horizontal asymptote in this one. Okay, so I don't have those. All right, so next thing I have to find is my mins and maxes and increasing and decreasing concavity. So let's find our first derivative and our second derivative. So we have a product rule in this one. Now, this is definitely one of those ones that you probably, I forgot that over too, are going to want to clean this up a little bit before you do the second derivative. So pull out what I can that's the same. And then what's left? The other thing that doing it, simplifying it down like that does, is it's going to allow us to find our critical numbers a little bit easier. So let's find my critical numbers for this one. So where is my critical numbers for the first derivative? Anyone? What are my critical numbers? How do I find my critical numbers? Yep. Or where it doesn't exist. In this case, it exists everywhere. So. Yep. So if we solve this one, so we have 2x minus square root of 5. So that's x equals square root of 5 over 2. And then the other one, x over 2 minus the square root of 5 equals 0. X is 2 square root of 5. And that one should look familiar because that was a 0 in my original function. So if we look here, that's a 0, right? So how many times is that a 0? What's the multiplicity of that? Anybody remember what multiplicity was? How many times that factor occurs, which is your degree. So that factor occurs 3 times. That means the graph goes through x at that point. Remember, the even multiplicity is where the function is going to bounce on the x-axis. And if it's an odd, it goes through it. If it bounces, that means it's a minimum or a maximum. Okay? Although if it goes through it, that means it's not going through that point. So we can tell that even though that's going to is a critical number, it's not going to be a minimum or a maximum because it's going through that point. And when we do our chart in a second to actually figure out over the intervals which ones are your minimums, which ones are your maximums, we will notice that aspect of it. The line is going to go through that one, that critical number. Yeah. So we have square root of 5 over 2 and 2 square root of 5. So let's plug in x equals 0, x equals 2, and x equals 5. What is this function? Let's write this out. So remember, one of the nice things about Desmos is you can type this in like this, and we can plug in numbers. And all we care about is if it's positive or negative. I don't care what the actual number is. So at 0, it's positive. At 2, it's negative. And 5, it's negative. So notice that around that point, it doesn't change direction. So while my tangent line there is 0, it doesn't go through that. It doesn't have a minimum or maximum. It's just going to go through that point. All right. Next thing I need to find is my concavity. Figure out where it's concave up, concave down. So, but we can go back to that graph that we have now. And I do need to plug in so what was the original problem? Hold on, the original problem. X is square root of 5 over 2. So this one came out to be a decimal, but I can change it to a fraction. I would check that first before you have to sit there and do it out by hand. So this one I can easily type in. It's 45 over 5 or for 8. So my next point is going to be square root of 5 over 2. And it was 45 over 8. All right, so let's take our derivative. Find my second derivative. So again, my same thing I would hold true. I would clean up as much as I can. So I can take out an x over 2 minus the square root of 5. And what's left, I have 2x minus square root of 5 plus 2 times x over 2 minus the square root of 5. So 2x plus x is 3x. Negative square root of 5 plus negative 2 negative 3 square root of 5. All right. So now where's my zeros? Same process. So x over 2 minus the square root of 5 equals 0. So x is 2 square root of 5. That keeps coming back up. And then 3x minus 3 square root of 5 is x equals square root of 5. So now we need to figure out concavity. So it's concave up, concave down. So 0, 3, 5. So it's negative at 0. At 3, it's positive. And at 5, it's negative. So it does switch concavity at 2 square root of 5. This doesn't switch direction. So we are going to need, because it switches concavity here, we need that point as well, because that's going to be our inflection point. So what was it? Square root of 5? Oh, good. That one comes out to be nice too. That's 10/3. All right. So we had, before square root of 5, we had concave down and increasing, correct? So concave down and increasing. To concave down and increasing. And then at that point, at square root of 5 over 2, it goes to decreasing, but it's still concave down. At square root of 5, it does what? It switches to concave up, but it's still decreasing. And then after 2 square root of 5, it switches to concave down, but decreasing. So at this point right here, it asks, is it a slanted tangent or a horizontal tangent at that point? So at that point, we had a tangent of 0, right? What happened at 2 square root of 5? That was still a 0, right? So that's a horizontal tangent. So that's a horizontal tangent. And for these problems, I'd always graph them. Make sure they look right. And it looks similar. Because they give you the graph, they give you the equation, so I can make sure it looks similar. I'm missing an inflection point somewhere? Inflection point. 5. No clue. But it was all there. I have, so on these topics, because this is the second mistake that I found with them. If you get a problem wrong and it looks totally correct to you, send it to me. Because I had at least one other topic the other day, I can't remember who told me. It was like they actually did it and it was totally correct. And I went and looked and they had the asymptote was off. They had the asymptote at 3 and it was supposed to be at 2. And it was graphed in the right spot, but their number was off in the actual table. So if you come across an error like that and you're like, this is totally correct and it's coming out wrong, just send me a quick email and I'll send it off to them. Because like nothing changed in that graph and now it's right. I have a sneaking suspicion these are a little more complex for them to actually go through and do them. So there's little errors because I'm finding them in my iBot where they're looking at graphs. That seems to be all the errors that come up in it is in the graph format. So, all right, let's do another one. No, let's not do that one. Let's do this one. Okay. This one has a slant asymptote. All right. So let's look at this. So your slant asymptote is this right here. That's your slant asymptote. So my slant asymptote is -4/3 x plus 3. So let's graph. Oh, we have to graph our points first before it will let me do anything else. Oh, no, I can do my asymptote. -4/3 x plus 3. So there's my slant asymptote. All right, let's graph our points. 0, 13/3. To a -1. All right. Do I have any other asymptotes in this problem? Yeah. So x equals 1 is undefined. So that means you can't do it. So that's going to be a vertical asymptote. All right. So now we just got to figure out the concavity. So -infinity to 0, it is decreasing, and concave up. From 0 to 1, it is increasing and concave up. One to 2, increasing, concave down. -2 to infinity, decreasing, concave down. And that's how you'd expect equation like with those type of lines to look. So it's either going to be in there or on the outside. It's literally, they give it to you in the problem right there. They give that to you in this topic. If they don't give it to you in its equation that you have to go through and solve, you do long division. Let's do. Let's do an exponential. Any domain restrictions? There's nothing in the bottom there. All right. So first thing we have to figure out is intercepts. So if we plug in 0 for x, what do I get? Yeah, because e to 0 is 1, so 0 and -8. So there's my y-intercept. For my x-intercepts, we would do 0 equals -8 e to the negative x squared over 100. Can that ever be 0? I think it's smaller, but it's never going to be 0. So there are no x-intercepts in this problem. And I have no vertical asymptotes. Do I have a horizontal asymptote? So what does this do as I go to infinity? So what does negative exponents do? The -8 really doesn't do anything in this problem, so I don't really have to worry about the -8. Oh no, that's why I was that's actually the important piece of this one. So if we look at just e to the negative x squared over 100, that's really saying the same thing as saying 1 over e to the x squared over 100, right? So as the bottom's getting infinitely large, so as x goes to infinity, f of x goes to what? So as the bottom, it's a fraction. So it's 1 over an infinitely large number. What is that? Going to 0. What about the other direction? As x goes to negative infinity, what's happening to this graph? It has x squared in it, right? So the x squared means that it's going to take care of the negative sign, so it's still going to infinity. Or it's still going, that's still going to infinity, so that's going infinitely large, so it's still going to 0. If the x squared wasn't there, that would change things. Because that would actually then flip it back over. All right, so we have a y-intercept and our horizontal asymptotes. Let's graph those. So I have a horizontal asymptote at 0. And I have an or y-intercept at 0, -8. So the next thing I got to find is my first derivative. All right, so where does this equal 0? Yeah, because the e can never equal 0, right? So the only time this equals 0 is when x equals 0. So we have one critical number at 0. So if I plug in -1 and 1, so this e right here, is that ever going to be negative? No, because it can never be 0, right? It was always there. So that's never going to be negative. So we don't even really have to worry about that part because I know that's positive. So if I plug -1 into this, what am I going to get? A negative answer, right? 4/5 times -1 is negative. So it's going to be negative. And when I plug in positive, I'm going to get a positive. So I know it's decreasing on the negative side and increasing on the positive side. All right. So next thing I got to do is what? Find my second derivative. Now this one I have to do a particle because I have two pieces. So I have 4/25. Yeah. All right. So where's the concavity for this one? So this part can never be 0, so I don't have to worry about that part. So I just literally have to worry about this piece. That's not nice. Oh, this is funny. So this one actually works out to be easier when you don't factor that piece out. Oh, that's what I did. Okay. I forgot. That doesn't go there. Okay. I love how when I erase something and people go, I didn't think that was supposed to be there. Yeah, good. It's all me. Because that makes this problem a lot easier. All right. So we've got x squared equals 50, which means x equals plus or minus 5 square root of 2. I'm looking at it, I'm like, there's no way they've made it that hard. All right, so we've got our concavity. So 0, negative 10, and positive 10. That works. That'll always be positive. If I plug in negative 10 here, we have 1 minus 2, which is negative. If I plug in 0, I get 1. That's positive. And if I plug in 10, I get 1 minus 2, which is negative 1. Because again, I don't have to worry about that first part. That's always going to be positive. So all I'm looking at is what sign that is. We do need to find the actual answer for 5 square root of 2 for the original problem at those points. And of course, it comes out to be a messy number. So if x is negative 5 square root of 2, we get negative 8e to the negative 50 over 100. So negative 8e to the negative 1/2. And if I plugged in 5 square root of 2, everything's exactly the same because of the square. So it also equals negative 8e to the negative 1/2. So you actually can type it in just like that, like with the e and everything else. All right, so we have decreasing concave down, decreasing concave up, increasing concave up, and decreasing concave down. And since these 2 points right here were not a critical number in the derivatives, then they're just slant asymptotes. I mean, not slant asymptotes, they're slant tangents. It's not a horizontal or vertical tangent. All right, we'll do one more of these. We'll do the logarithm one, and then we'll do that. So this is no different than the other problems. It's just a logarithm problem. So plot our point. 0, 0. And there's one more point on this one. We have it an inflection point at that point, and inflection point and a horizontal tangent at that point. But we don't have to graph those extra points. Do I have any asymptotes? Not the. So if we look at this, do I have any asymptotes the way this is worded right now? I don't have anything that says undefined or anything there, but look at the range of values. Where does it start? Right. All the rest of them we started at 0. Or I mean, infinity, negative infinity to positive infinity, right? This one starts at -3. That means I have a horizontal asymptote, or not a horizontal, a vertical asymptote at x equals -3. And if you think about logarithms, they don't typically go below 0. So there's an asymptote, a horizontal asymptote in the parent function at the y-axis. So in this case, you're going to have that. It's just going to be shifted somewhere. In this case, it's shifted to -3. All right, so from -3 to 0, it is decreasing and concave up. From 0 to the next point, it's decreasing and concave down. Now, at that point there, what kind of asymptote do I have? Or which kind of inflection point? Do I have a horizontal tangent or a slant tangent at 0? It says 0. That is a horizontal tangent. Then from this point on, I have decreasing and concave up. And at that point, there's no derivative there. So I have a slant asymptote. Any questions with those? They're just going to be a pain. For the ones that give you the equations, I would highly suggest graphing them on Desmos. See what they look like. Again, you're not necessarily going to be able to use it to find the points because not all the points are going to be nice. But you can get a general idea of where they are. So when you're doing your calculations, you can use that to help you figure things out. Okay. So definitely take advantage of that. All right. No other questions. I will see you next Tuesday. It's election day next Tuesday. Yeah.
November 6th.
Yeah. It's always the first Tuesday in November. This is the election that everybody always forgets about because it's not a presidential election and it's not a congressional election. It's a local election, which, in all honesty, is more important than every other election you do. Yeah, you can actually, and you actually have a typical say in what goes on in your town, unlike what's going on at the federal. So go vote.
Can I have for the next census?
The Thursday.